Our next talk is by Professor Claire White. Professor White has a joint appointment between the Andlinger Center and the Civil and Environmental Engineering. Her bachelor's and PhD degrees are from University of Melbourne, and then she did a postdoc at Los Alamos National Lab. In 2012, she was given the Outstanding Student Research Award from the Neutron Scattering Society. And in 2013, she joined Princeton, and she is interested in understanding and optimizing engineering and environmental materials, including low CO2 cements. And this research spans multiple length and time scales. It utilizes synchrotron and neutron-based experimental techniques. So please welcome Professor White.
Thank you for that very nice introduction, and it's a pleasure to be here today to be able to share with you some of the research activities that my group has been doing, and also just to introduce the idea of what is sustainable cement. So this is a material that I think is very underrated in terms of a complex materials science, but also something that's used so extensively around the world. We don't understand, well, we don't have a really good handle on the sustainability issues associated with cement production. So the first question is, what is concrete? And so I put up this slide just in case for those of you who go out to your sidewalks and say that's cement. No, it's actually concrete. So the way that concrete is made is that we have this cement powder here on the left. It's called Portland cement powder. And you add water and you end up with a paste, but the paste is mixed with sand and rocks to get your concrete. And so you might think, well, we understand this material fully, completely, utterly, because we've used it for over 150 years. But in reality, there's a lot that we don't know about Portland cement concrete. One thing that a lot of people don't know is that it's got a sustainability issue, which I'll get to in a minute. But when it comes to concrete, there's a lot of interesting things we can do with this material. It's the basis of almost all types of concrete used in the world, this Portland cement concrete. It makes up about 95% of all concrete that's used in the world. And a lot of people say, is this the closest thing to magic the human race has ever invented since sliced bread, right? And the reason this is the case is it's such a versatile material and it's used so extensively around the world. You've got examples like the Hoover Dam, okay? This was a monumental construction project, and this is Portland cement concrete. You've got things like tall buildings. In Dubai, there's this really tall building, I can't pronounce the word at the moment, which has been made out of very strong, high-strength concrete. There's also examples such as in my hometown in Melbourne. There's a bridge that's called the Balti Bridge. These are called goalposts because we play Aussie rules football over there. But this is all made out of concrete. And you can see that it's a very versatile material and we often take it for granted. There was a similar type of concrete that the Romans and the Greeks used thousands of centuries ago. And this is the Pantheon in Rome. And so you can see that there's similar types of materials that people have used over centuries. So you might think this is a very boring subject to be talking about. How can we be talking about concrete today? Well, to make concrete, you have to make Portland cement powder. And this is a very vertically integrated industry. The process of making cement powder is you dig limestone and clays out of the ground in a quarry. You do a lot of pre-treatment to this stuff, including grinding, and then you put it in this very high temperature kiln where a lot of chemical reactions are occurring. Now, one of the chemical reactions that occurs in this kiln is the decomposition of limestone being calcium carbonate. So when you decompose limestone to get a calcium oxide phase, you're releasing CO2 into the atmosphere. Not only are you releasing CO2 into the atmosphere, but you're also needing to get to really, really high temperatures, 1,450 degrees Celsius to be exact, to make the phases that are reactive in Portland cement powder. And so combined with the high temperatures and the chemistry that occurs releasing the CO2, A conservative estimate of how much CO2 is produced per tonne of clinker that comes out of your plant is about 0.8 tonnes of CO2. So it's almost a 1-to-1 ratio between the amount of CO2 that is emitted per tonne of stuff that comes out of this manufacturing process. Now you might think, oh well, this ain't so bad because, you know, we don't really see cement on the CO2 emission scale, but actually President Ralph Cicerone back on Wednesday had cement on his CO2 diagram of the emitters. So what you find is that cement manufacturing accounts for 5 to 8% of all anthropogenic CO2 emissions. So that's not small. It's still there. It's something that we have to be worried about and something that we need to address in the near future. And with concrete being the second most used material after water and going to double by over the next 30 years or so, it's a problem that we must address. And so this, from the International Energy Agency, has been put into reports, and they've come up with solutions about how this is going to be addressed. And there's a number of ways that people are thinking about mitigating these CO2 emissions, but the majority of them are based around the chemistry of Portland cement concrete. On the right here, we have things like energy efficiency of the kilns, alternative fuels for the kilns, what's called clinker substitution. So you're trying to reduce the Portland cement powder, but you might not be able to reduce it to the same extent that alternative cementitious materials how they exist. One other thing I want to point out is this carbon capture and storage. The report was saying that for every new cement plant that is built around the world, there should automatically be a carbon capture and storage plant built right next door. This is a very expensive endeavour. And so, as you might have heard throughout the symposium, there was a couple of mentions about carbon capture and storage, and at the moment the costs are just way too much to really utilise this technology fully. So one other thing that I put down here in the report, not by myself, I just kind of tagged it on, was that we also need to look at these alternative cementitious materials. And this is kind of a game changer. This is a disruptive technology because we are getting away from Portland cement chemistry. We're getting away from what the cement industry is all based around. And so this disruptive technology is having fun trying to penetrate into the marketplace. And I'm going to try and convince you where key fundamental research, both science and engineering research, holds the key to be able to help the penetration into the marketplace. So firstly, what are some of these alternative cementitious materials? Well, we're working on something called alkali-activated materials. Instead of using Portland cement powder, we're using either industrial byproducts or natural clays that we do a very mild thermal treatment to. And these powders are called aluminosilicate-rich powders. We activate with an alkaline activator to get something that pretty much looks exactly like Portland cement concrete. The industrial byproducts are waste products. So we're reusing stuff that sometimes otherwise ends up in landfills, such as coal-derived fly ash. So we have a problem in this country with fly ash. Fly ash is ending up in these ponds, these storage ponds, because it's very hard to dispose of this material and it's not being utilised to its full potential as being reused as a waste material. And so this is some of the stuff that we can be doing, is we can not only be making more sustainable products, but we can also be addressing the issues with waste materials. So just to convince you that it's not just in the lab that these materials do work, here's an example of a small startup business in Australia that was using these alkali-activated materials early in the 2000s. And this down here is an alkali-activated concrete base on which these silos are built. You can also make things like precast panels, sidewalks, all of that kind of stuff. So what's the issue? Why hasn't this product penetrated into the marketplace? It comes about from the conservative nature of the cement industry. It makes sense that from a construction perspective, we have regulations, because you don't want to have your building built out of some new material that hasn't been proven that it can last for 50 to 100 years. Now, we do have the data, a small amount of data that shows that this material does last 50 to 100 years, but that data is not extensive enough to be able to change the construction standards at this point in time. And so that's where the research is really necessary to create this data so that then we can get this new material into the marketplace. So it's essentially the long-term performance of these new types of concrete are not well established. And this has implications for the use of the technology because we don't satisfy the current standards and codes enabling the use of this class of concrete. So what we really need to do is be able to predict the long-term performance. And there's the key for fundamental research to providing this information. And so today I'm going to talk about two projects that my group has been working on recently to address this issue. The first is looking at the pore structure of these new types of concrete. The pore structure is what controls the ingress of ions into the material, and these ions are what degrade the material from the inside out. So if we can understand that pore structure, if we can understand how easily the ions can ingress into the material, then we have an idea of how the material is going to perform over the long term. The second thing, and this is a little bit outside of the box thinking, is we really need to understand the atomic length scale structure of this material. If it's not as stable at the atomic length scale, there's the potential that it's going to change over time. And if it changes over time, then this can lead to degradation as well. So objective 1 is to look at the pore structure of this material, and objective 2 is to look at the instabilities at the atomic length scale. I should mention that because I'm only limited to 20 minutes today, I'm not able to show you the plethora of research that my group has been able to perform over the last 3 years since we've been here. But just to give you an idea, here is a little bit of a schematic that shows some of the different techniques that we use. And we're looking at stuff going from the atomic length scale up to the micron and above. One thing I might get asked during question time is, what is the strength, mechanical strength of this material? Let me just tell you that we can tailor the mechanical strength. High strength, low strength, all of this kind of stuff. That's been proven, that's been shown in previous research. It's the long-term performance that we're really grappling with at the moment. And so that's what my group has been focusing on here at Princeton to really understand so that we get that data so that then we can use that to change the construction codes. So the first research that I'm going to show you is looking at the pore structure of these alkali-activated materials using a non-destructive technique. And it's called beam bending. It's where we have a very thin rod of the cement sample and we put it into 3-point bending, where at both ends of the long sample we have supports, and then we're putting a force in the middle of the sample. When we put that force on the sample, we're putting the pores out of equilibrium. The water that's in the pores is put out of equilibrium because some of the pores are put into compression, so they shrink, and some of the pores are put into tension. And so what happens is water's going to want to flow through the material to re-establish equilibrium. And that relaxation, that flow, is called hydrodynamic relaxation. So that's what I want to take for you to take out of this slide. There's also something known as viscoelastic relaxation, and that's due to the solid structure of the material. We're not going to go into details of that. So you're just going to concentrate on this hydrodynamic relaxation, which tells us about how quickly does water flow through the pores in a cement material. Now, I would love to have said that I've done all this research, but there's a lot of important people that have been involved. The first person to work on this was my master's student, Catherine Iben. And then Anna Blythe, who's of the class of 2019, she's been doing some of this research. So she's an undergrad here at Princeton. And also Bridget Zakruski from the class of 2017. She's also been involved in this research. And I have to say thanks to George Scherer, who is a professor here at the university, who's been applying this technique to Portland cement concretes. And so we've now been able to apply it to alkali-activated materials. So these are the results. I can't give a research presentation without showing results, right? So here's some results of what a beam bending experiment looks like. Essentially, you end up with a load decay, the black curve here, which is as a function of time, and the time axis is on a log axis. And so what you find is there's an inflection point that shows up, if you can see this in the data. And we can fit the data using the hydrodynamic relaxation component, which I told you to take note of, and also that viscoelastic one, which I told you to ignore. And so essentially what we're trying to look at is this inflection point, which gives us an idea of how quickly does the water flow through the pores. Now, we're firstly going to look at a type of alkali-activated concrete that's made using blast furnace slag, so a waste material. And we've activated it using two types of activators. There's a sodium hydroxide and a sodium silicate. And we want to see if the type of activator has an impact on the pore size and therefore the relaxation time. So here's some experimental data. On the left, you have these relaxation plots for the hydroxide-activated slag. And what you find is the inflection point, and I can't really see from this angle, but I'm pretty sure it turns up at around a couple of seconds. So it's quite quick. The other thing you can see is the inflection point moves to the right with time, which tells you it's taking longer for the relaxation to occur as the sample gets older. So that's telling you that the permeability, how quickly the water flows through the structure, decreases as the sample gets older, which makes sense. Now, if we look at the silicate-activated slag sample, what you find is that inflection point has moved to about 10,000 seconds. So it's 4 orders of magnitude higher compared to the hydroxide-activated sample. So that's telling you that when we change the activator, we completely change how quickly the water flows through the pores. And so from this, I can tell you that the silicate-activated slag sample is has a lot lower permeability compared to the hydroxide-activated sample, and therefore this one is better from a durability perspective. This is what we should be using when we make new types of concrete, because it's going to take a lot longer for the ions to degrade the material from the inside out. Just to show you the effects of the activator, not the activator actually, the precursor on the permeability, we also looked at calcined clays such as metakaolin. So we're changing now the precursor and keeping the activator consistent. And so what you find with an alkali-activated metakaolin is now you're back to an inflection point that's of a couple of seconds. And so this is telling you that the alkali-activated metakaolin is a lot more permeable compared to the alkali-activated slag sample. So this has significant implications for the long-term durabilities of these materials. And what I find really nice about this is that at Princeton, we've got these undergrads that are really interested in the research, and these are the people who've been performing these experiments. Not me, not my postdocs, not my grad students, but the undergrads. So from this, we're able to compare the permeability results from Portland cement concrete, where there's a value here on the right. If we compare it to alkali-activated slag, we're only comparable if we have the silicate in the solution. We don't want to use a hydroxide activator. If you then look at metakaolin, we don't want to use the metakaolin because the permeabilities are nowhere near that of Portland cement concrete. And you can also look at later times to find that the permeabilities of this silicate-activated slag decreases with time. So I hope I've convinced you for the permeability results that we can look at the durability of these materials using some key experiments in the lab here at Princeton. Now, the second part that I want to quickly go through today, because I see I've got 2.5 minutes left, is to talk to you about the instabilities at the atomic length scale and how we're really getting at whether the atomic lengths, the atomic bonding and the atomic structure of alkali-activated materials, whether they're as stable as what's in Portland cement. And so what we need to do is we need to understand atomic structures, and we know what's pretty much in Portland cement concrete. We have an idea of what's in alkali-activated materials, and there's issues with this water, which I just showed you in terms of permeabilities. But we want to get at the atomic length scale structure. And so to do this, we tend to have to go to large experimental facilities, such as the Advanced Photon Source shown here at Argonne National Lab, or places like the spallation neutron source at Oak Ridge National Lab. So here what we're doing is we're using X-rays, which are generated by this large storage ring, and essentially shooting them at our sample to do diffraction. And diffraction looks at the atomic structure of the materials. The key thing that we're doing is that we're not looking at what's called the diffraction patterns in reciprocal space, and that was a bit of something to get out of my mouth. I want to try and explain it more succinctly. What you find is you end up with this data, and what happens if we take a Fourier transform, we go from what's called reciprocal space into real space. And the real space is telling us about all of the atom-atom correlations in the material. And that's important because it's telling us about the atomic structure of the material, and I think Lynn's very excited because she dropped her phone. Yeah. And so here on the right, we have a paired distribution function shown for SLAG, which shows that it has local ordering but no long-range ordering because all of these correlations die off by about 10 angstroms. So we've used this technique to look at materials, and before I show you the actual results for the materials, I want to convince you that we can see the difference between a crystalline material that has average ordering over the long scale, a nanocrystalline material, which has an average size governed by, say, the size of the particle, or an amorphous material, which only has local order and no long-range order. So here's shown 3 types. There's the crystalline, the nanocrystalline, and the amorphous. The crystalline goes out to like infinity on the x-axis. The nanocrystalline sample dies off with a particular die-off that's governed by the size of the particle, and an amorphous material, you're really losing those correlations by about 10 angstroms. So now if we look at Portland cement concrete, and that's essentially what I'm showing here on the right with a lot of different terminology, but essentially what you see is things die off by about 40 angstroms. So that's telling you in Portland cement concrete that the ordering is on the length scale of about 40 angstroms or 4 nanometers. If we go to alkali-activated materials, what you find is things die off a lot quicker by about 10 angstroms. So this one's amorphous. The next one, alkali-activated slag, which I showed you for permeability, is also predominantly amorphous, whereas if we lay over the Portland cement concrete, you find it's mostly nanocrystalline. So this is telling you that the atomic ordering in these cements is intrinsically different, and it might have implications for long-term stability of the materials, because the more crystalline you are, the more thermodynamically stable the material is. And so this is shown here on this slide that it's more nanocrystalline in a Portland cement concrete compared to these alkali-activated materials. And this might have correlations with long-term properties, long-term issues, or short-term issues such as microcracking. Now, I can't go into the details, but we're further looking into this problem, and I had like another 10 slides, which I don't have time to go over, so I took them out yesterday. But essentially, we're looking at this now using computational chemistry, and we want to get a real understanding of what is the implications of doping the structure with certain types of elements. Because we do have differences in the chemistries of these systems, and we don't have a fundamental understanding of what is the implication of these differences. So we're going at it from a computational chemistry point of view. So in conclusion, I hope I've convinced you that we can look at the long-term durability of these new materials by looking at the pore structure. We also have to understand these instabilities at the atomic length scale, and so we've been doing that using both experiments and theory. And I hope I've convinced you that this alkali-activated material poses as one option in a suite of potential solutions. I want to say that again. There are many solutions to solving this cement issue, with alkali-activated materials posing as just one of these options. But we really need to have that fundamental understanding if we're going to have that penetration into the marketplace. So with that, I'd like to thank funding. It includes the Andlinger Centre through some of these internal grants, and the National Science Foundation, and all the people in my group for actually doing the work. Thanks.
One question, many of these waste products is wonderful, the idea of being able to recycle the waste products into these alternative cements, but many of them have heavy metals in them. What are the prospects for filtering those out, sequestering them, making sure that you're not producing something which will cause later environmental harm?
That's a very good question in terms of the heavy metals. So this has been studied not by my group, but by other groups in terms of leaching studies to see if you are leaching out heavy metals. And one thing you find in some of these systems, Portland cement has been known to for waste immobilization for radioactive elements. But for the alkali-activated materials, say in fly ash, we do have heavy metals. And so the leaching studies, the ones that are out there, show that most of the heavy metals are immobilized, but that does require additional work because we don't want to be making materials where in 10 years' time stuff starts coming out of it. I would say that the research shows promising results, but additional research is required.
So you'll forgive me for asking a really naive chemistry question. So a lot of companies come and talk to me about crazy ideas that they have. And so this one group came to me that has a technology for capturing CO2 from the air. And the claim is that they believe that they can sequester CO2 in place of rebar in concrete. So I know I'm putting you on the spot, but is there anything that makes sense to you about the introduction of CO2 into concrete that would provide the substitution for rebar?
I hadn't heard of the rebar one before, but I have heard of carbonating particular cements to make concrete. So there are startup companies around there that are using calcium silicate starting ingredients, and then instead of adding water, they're adding CO2. And so that converts into calcium carbonates. And calcium carbonates tend to be pretty stable if you end up with the calcite form. So they're looking at the whole concrete being made up of these calcium carbonate phases instead of what we usually have, which is calcium silicate hydrate gel. Now, I hadn't heard of the rebar. So whether they're trying to... So the one thing with rebar, and this is what I teach my undergrads, is that reinforced concrete, the rebar is to take up tension. Now, if you're sequestering in CO2 and you're forming calcium carbonate phases to act as rebar, that doesn't take tension. It's strong in compression, but it's not strong in tension. So I would be interested to see how they're taking the tension up in their materials by using calcium carbonate.
The starting material of your process is SLAG. This could be very important. How could you then determine the characteristic of the final product? This starting material vary largely.
So the question was about the ground granulated blast furnace slag and the fly ash and the heterogeneities or in the materials and also the variability from source to source in the starting materials and how that impacts what we end up with in the material. And this is a very good question and something that we're trying to address in the research. So what we tend to do is when we're looking at these materials, we're not just using one source of slag or one source of fly ash. A recent study that was done in my group was actually using 7 slags from 7 different parts of the world to try and look at the variability in the chemical composition and what impact this had on the final structure. And essentially we found that the structures that formed were slightly different but not significantly different. That was for slag. Fly ash is another can of worms because fly ash is a lot more variable, and even now they're using things like ammonium to pull out NOx in coal combustion for the coal power plants, and this is having an impact on the fly ash. So I think this is an area that really needs more research so that we can engineer ways to use the materials, including the variabilities.
Daya from Rutgers. I saw one of your posters yesterday, and regarding this impact of nanoparticles, specifically zirconium dioxide, atomic structure of traditional and modern cements. Now my question is, why zirconium dioxide? There are many other nanoparticles. Did you do research on this aspect of this atomic structure of?
Yes, so the question was types of nanoparticles in cements. And so what we've been looking at is there a way that we can tailor the atomic structure using a very, very small dosage of nanoparticles to make it, say, more ordered. And so we have been looking at other types of nanoparticles. We want the nanoparticles to be inert. We don't want them to be reactive because then they would lose their seeding aspect. So we have looked at titanium dioxide and zinc oxide as well.
Dan Steingart from ACE and MAE. Really nice overview, Claire. So when you talk about uncertainty and the failure mechanisms of the concrete, is it sudden? So when this stuff has been used in its largest format yet, what has the failure mechanism be, and is it graceful or slow, or does it very quickly lose strength? Let's say in like a brittle to ductile transformation. I'm trying to think of some analogy, but I just don't understand the nature of the failure mechanisms here.
So most of the failure mechanisms come about due to, say, chemical degradation that then affects the mechanical properties. It would fail in a very similar fashion to traditional concrete, where you get a lot of warning that, say, the rebar's been corroded first, and then you have times to mitigate the issue.
So the corrosion of the rebar is like a canary.
Yes.
So if there isn't rebar, what do you do? What else tells you?
Well, we haven't actually pushed to failure structures, and so structures that have been made out of these materials show as good as durability as Portland cement concrete. So there are examples in the former Soviet Union where they built apartment building blocks out of carbonate-activated slags. They're still standing today. So when it comes down to how exactly does it fail, if we're waiting under natural conditions, we could be waiting hundreds of years.
But I guess to get to the punchline, there's no. It's a similar treatment, so you can drop it in and you can use the same equipment and you can expect the same kinds of degradation as you would in Portland. There may be different underlying fundamentals, but the continuum effects would look the same.
Correct.
Barry Rand from Electrical Engineering in the Andlinger Center. My question is about the bending test you guys do to get at the permeability. Presumably that's an accelerated sort of lifetime test. Is there a way to correlate the permeability value with how long it will live in real world application?
So the permeability test is just to have an idea of how quickly does water move through the structure, and this tells us about mass transport of ions. So it's not actually an accelerated test. It's a test to get at the intrinsic permeability values without using force, like applied pressures. I know it's a force experiment, but usually it's people trying to force liquid through the material, whereas this one's just allowing it to relax and for the liquid to move through. So this test is not accelerated, but there's a lot of tests that we do that are accelerated, like carbonation, reaction with CO2, sulfate attack, chloride attack of the rebar. There's multiple others. And the real thing that we're trying to get at is the atomic scale mechanisms of those degradations. We can do that experimentally through accelerated, but the long-term idea is to tie these in with simulations, where with simulations we can do both the accelerated level and the natural levels and really try and get at the degradation mechanisms, not only from accelerated testing, but also the fundamental natural degradation mechanisms from computations.
Okay, thank you, Claire.